All right, we're going to talk about differentiability. That means when a derivative exists. Well, there are four cases where a derivative does not exist. In our first situation here, we call a corner. So if you were to think about the absolute value function, which we have sketched here for us, we say that at this point of interest where x equals 0, we have a sharp turn or a corner. So we say that the one-sided derivatives differ at x equals 0. In other words, if you were to look at the slopes of the tangent lines on each side of x equals 0, you get different values. So that means at the point x equals 0, there's no way for the derivative to exist. So to write this out using some notation, we can say that the limit of our derivative as x approaches 0 from the left, that's what we call the left hand derivative. Okay, let's suppose we are talking about the absolute value function. Oh, hang on, buddy. Sure, here you go. Sorry about that. Suppose we're talking about the left-hand side as x approaches 0 from the left. Well, if we're talking about the absolute value function, then our slope would be -1. And if we were to look at it from the other side, the limit of our derivative as x approaches 0 from the right, and this is known as our right-hand derivative, okay, this would be +1 because you can see the slope there is 1. So they don't match up at 0. So the idea here is we say the derivative does not exist because we have this sharp turn, also known as a corner. All right, so why don't you jot down that this sometimes is referred to as a sharp turn. Okay, our next example where a derivative fails to exist is called a cusp. Sometimes this is referred to as an extreme case of a corner. A common example of a cusp is the function y equals x raised to the 2/3, and I've sketched that for us here. You can see how it's kind of bent. It's not quite the same as the corner that you see in the absolute value of x function. The idea here is we still don't have those left and right hand derivatives matching up. So here at x equals 0 we have a cusp. If you were to think about your tangent lines as you get closer and closer to x equals 0 on each side, well, on the left side it would be pretty darn close to being vertical, but really it would be -infinity since there is a negative slope there on the left hand side. And on the right hand side it would be +infinity. Again, it's getting extremely steep, but it's not going to quite ever be vertical. So the two one-sided limits once again don't match up. So a cusp is a situation where it's kind of curved like that, and once again we do not have the derivatives matching up on each side of it. Okay, our third one here you probably are already aware of. It's a vertical tangent line, and recall if we have a vertical tangent line, it really means that we have no slope. No slope really means we have an undefined situation. So if we have y equals x to the 1/3, at this point where x equals 0, if you were to draw in a tangent line slope, for that split second at x equals 0, it would get perfectly vertical. So it does not exist at x equals 0 because the tangent line would be perfectly vertical. So the function value exists, but the slope does not. We can see that f of 0 is 0, but f prime of 0, the derivative, that does not exist. Okay, because once again there is a vertical tangent line there. Okay, so x raised to the 1/3 is a classic example of having a vertical tangent line. Okay, our fourth and final example of a situation where a derivative does not exist is when we have any type of discontinuity. So if a function is not continuous at a point, then the derivative does not exist. So I've drawn three examples here where in the first one we have the case of a jump. Now notice the point is defined here. Okay, we have a filled in circle, but that doesn't matter. The fact that it's not continuous, because we have a jump there, we know that the function is not going to have a derivative because it's not continuous. In my second, so let me just jot down jump. In my second example over here, we have a hole. Okay, so that is another example of a discontinuity. And even if we saw a random point above or below it, still wouldn't make a difference. It's still not continuous. So the derivative cannot possibly exist if it's not continuous. And in our last example here, we have a vertical asymptote, which once again is a discontinuity. So it would be impossible for the derivative to exist at that point. Okay, and finally, here is an important phrase to keep in mind. Differentiability, so the fact that a derivative exists at a point, that guarantees that the function must be continuous at that point. So if a derivative exists, we know that the function is continuous. So differentiability guarantees continuity. However, but the converse here is not going to be the case. Being continuous, so continuity, that does not guarantee differentiability. So just think about an example we saw earlier, whether we're talking about a corner or a cusp. Okay, these are continuous, but they are not differentiable. So just because a function is continuous doesn't guarantee that a derivative is going to exist. However, again, if a derivative exists, we know that we can work backwards and say that it is going to be continuous.